Relativity. It's not as strange as you think. It's even stranger. In part 1, we looked at how relativity made us disagree about things like time and distance, sadness. But in part 2, we found an even deeper bedrock of agreement, not just constants, but invariants, quantities that stay the same for all observers. Joy. But who cares? With all due respect to the athlete and the farmer, these effects only show up at crazy fast speeds. Classical physics works just fine for the rest of us. And we can't see relativity in our everyday lives. Can we? We can! One way we can see it is magnetism. So the goal of this video is to show that electricity plus relativity equals magnetism, and to bludgeon you with equations. You have been warned. First, what is magnetism? Electric currents create magnetic fields. They put forces on compasses. They follow the right-hand rule. And they follow this equation. See that magnetic field? A charged particle moving through a magnetic field will feel a force. This is magnetism. Currents cause magnetic fields. Moving charges in magnetic fields can feel forces. In this case, the force on the charged particle is up. It is attracted to the wire. Our two equations together. This is what we're asking relativity to give us. This equation, F equals QV m0 I over 2 pi r, is really not as bad as it sounds. The wire makes a field and the field pushes the charge. But notice our insistence on motion. If the charges stop moving, magnetism stops happening. Motion, velocity, remember, is what makes relativity's Lorentz contraction do its thing. So this is where we're going. And how do we get there? With electricity and relativity. Here are two of our favorite equations from those topics. Unfortunately, these equations won't cut it. Coulomb meet Gauss, and we'll need the velocity addition formula for relativity. Yikes, more on that guy later. So let's get to it. Looking at those charges inside the wire, but charges aren't enough. We need to have a current, so they need to be moving. And we'll say that inside the wire, the negative charges are moving to the left at speed u, and the positive charges are moving at the same speed to the right. I'll explain why in just a second. First, linear density, coulombs per meter, multiplied by velocity, that's multiplied by meters per second times coulombs per meter. Yeah, that gives coulombs per meter, that gives current, and we multiply by 2. Okay, next. Bring on the relativity. If those charges are moving, then the distances between them will be squished. And we are juggling now between two different reference frames. And that will be our main challenge in this video, and that challenge will get worse. And that explains why you couldn't just say that the negative charges are moving while the positive charges stand still. You see why? Well, that would cause the wire to appear negatively charged in the lab reference frame. If only the negative charges were being squished, it would look like it was negatively charged, and that can't happen. We need an overall neutral wire in the lab frame. That's what we see. If it looked negative anyway, positive charges would come rushing towards it. Wait a minute, isn't that what's happening? Yes, that's kind of the punchline. That's kind of where we're going. But anyway, we agree. In the lab frame, the wire has a current in it, but the wire is neutral. But the lab frame isn't the only frame of reference we need to worry about. We have 3 reference frames. And when we say wire, we're really talking about the charges inside the wire. So we have 4 reference frames to worry about. The positive charges moving one way, the negative charges moving another way, which isn't too bad if you're starting with the lab frame. We already know velocities u and v. But what about changing from q's reference frame to the frames of the charges in the wire? That's going to be tough, and we care a lot about what q feels. Q is going to feel that attractive force, that magnetic force somehow. But why is that going to be tough? This is what the situation looks like from the lab's reference frame. But this is the same scene from the charge's point of view, from Q's point of view. Not too bad. If you ignore relativity, finding the speed of the negative and the positive charges would then be pretty easy. The negative charges have a larger speed, more squishing. So overall, charge Q sees the wire as negatively charged and is attracted. Not true from the lab frame, but it is true from Q's frame of reference. Magnetism is born out of relativity, and we can quit and save ourselves all the gory equations for the sake of humanity. Quit now. You've been warned twice because it's about to get ugly. Velocities don't add up easily with relativity, and we'll derive an equation for that in just a moment. We'll need that equation to find the speeds of the negative and the positive charges in Q's frame of reference. So here we go, and if you don't care about deriving this combined velocity expression, skip ahead to 8 minutes, 50 seconds. First again, why do we need this thing? We don't. For small velocities, we don't need it. They add up nicely, but this can't always be true. If it was, you'd find velocities faster than the speed of light. No way. So let's take a closer look at what the Martian and the space traveler see, remembering what we know about time dilation and length contraction and baseball. Both the Martian and the space traveler are pitchers, but the Martian sees the ship's field as squished, and turnaround is fair play. The space traveler sees the Martian's field is squished too, but there's a difference. The Martian sees the field as moving away from the pitch, so the Martian sees that the pitch has to catch up to the field that's running away from it. The space traveler sees the opposite. That's what these equations say. But there's a lot packed into these two equations. We'll go through them bit by bit. xm. The distance to home plate as seen by the Martian is equal to gamma times quantity xs, the distance to home plate as seen by the space traveler, plus vts, the distance the ship moves during the pitch. Got it? And the same idea is used here for xs, the distance to home plate as seen by the space traveler. The problem is that we have to worry about two quantities, distance and time, and two different frames of reference. But we've got these equations, these two equations to help us, and using substitution, this is what we're trying to get. This Tm is what we're trying to get, and after that, we'll be in the clear. So, here we go, starting with xs. And substitution. Math. 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 Put it on top, breathe, and harder now, math. 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 Pause. Now we're going to take a break and prove this. And I told you this was bad, I wasn't kidding. This is a special proof about this weird gamma term that we'll use to get Tm in order to get an expression for relative velocities that we need to get to our argument about relativity and electricity. Welcome to the rabbit hole. Again, we're trying to get this. Don't give up hope. And that thing we said about gamma is true, I guess. I think. Anyway, I'll use it in the center there. Substitute. And we have it. We have Tm. We wanted Tm. Why did we want Tm? To find velocity. And velocity is equal to distance divided by time. Always has been, always will be. Now this kind of makes sense, so take a close look at that expression for xm and tm. Got it? Divide them, then multiply in order to rearrange and simplify, and that's it. The speed seen by the Martian, nothing too complex, just the distance seen by the Martian divided by the time seen by the Martian. That's it. Relativistic combined velocities working together, or working against each other. That was a headache. It's about to get even worse. But now we know the speed of the positive and negative charges relative to Q. Too bad we don't really care about speed. What do we care? We care about gamma, the extent to which the distances are squished. That way, if we know gammas, we can find the net charge density of the wire. Gamma for the negative charges will be bigger, because that has the speeds working together instead of working against each other. So here is our next major challenge, taking what we know about gamma and what we know about velocity and putting them together. Start by squaring both sides and move step by step by step back to the top. Down, 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 back to the top. Getting smaller. Looking good. Remember this? Let's use it. And we're done. expressions for gamma. Nice ones too, if I might say, and I feel like I made that more difficult than it needed to be. Oh well, remember this equation for net charge density? Good, because it's about to get blowed up. And subtracted down. Looking good. But who's doing the looking? Q's doing the looking. This is the charge on the wire, the net charge on the wire as seen by Q. He sees it as negative and is attracted to it. So our challenge now is to turn a charge density into an electric field, and then that electric field into a force. This seems like something we can do, but we're going to need help. Gauss, a little help here, please? If you don't know Gauss, this might look fancy. It's nothing too fancy. It's just the electric field around a charged wire. Charged wire? It doesn't look that way in the lab. In the lab, the wire is neutral. But to Q, the wire looks charged. And this is what he sees. An electric field, E sub Q. The field seen by Q. But notice that we got a gamma naught term. What's that? Oh, I remember him. Hey, looks like we can simplify this thing a bit. Wait a minute. Are you sure? Yes! Don't go soft on me now. The moving charges are squished in the lab frame. We can do this. We can, and we will, and we did. And now, I know what you're thinking. You're looking down at the square root term in the denominator, and you're thinking, again, we can simplify this with gamma. And then you're thinking you can plug in lambda q, and you're wrong about that. We could do that, but we won't. Instead, we're going to take aim at the EQ term. We've been focused on the charge frame of reference for so long that it's easy to forget that we want a final answer in terms of what the laboratory will observe because, we work in a laboratory. In this case, it will see a stretched, less intense field. Wait a minute. I thought you said, wait a minute, wait. There's going to be an electric field, a less intense field, but an electric field in the laboratory? No way. I thought you said that there was no net charge on the wire in the lab. And there isn't, and I'm not saying there is, but I'm saying that whatever Q sees in his frame, you can call it an electric field, you could call it a magnetic field. See, this is where the magic happens. This is where relativity is making a magnetic field. You could call it an electric field or whatever Q is seeing in his frame, that same thing will be stretched in the lab frame. And if it makes your head spin, just trust the equations, and bam. You've found this expression for E lab, the electric field in the lab. Although I guess we should call it a magnetic field in the lab, because in the lab it looks like a magnetic field. But that's what it is. It's going to, whatever it is, call it electric or magnetic, it's going to put an attractive force between an upward force on that charge. It's going to push that charge up towards the wire. Whatever it is, we're going to use it, rearrange it with these expressions into this. Hold it for just a moment. F equals EQ. And we're done. We made it. The force of attraction between the current carrying wire and this moving charge Q. Magnetism, born of electricity and relativity, and a lot of equations.